Okay, let me get a handle on my stream here. First, I want to make sure that my voice is coming through. Okay, that's okay. I'm streaming through Twitch, but I'm also trying to stream through YouTube as well. And I went a second ago and it shut down on me. My stream did, so let me check here now. Looks like I'm live. Okay. All right. Interesting thing about the YouTube live as I'm looking at it, it's blurry, whereas the Twitch goes straight to 1080 and is fine. So I'm not sure why it does that. And it might not do it on your end. But let me double check. Yep, there it is. So my stuff's coming through on here too. So I'm going to push forward anyway and see if I can get through this. And what I'm going to talk about first is conditional probability. So I'm going to extend what we talked about last night in class. I have a problem here that I love doing. That is about knowing a murder victim. But before I set that up, let me get everything here on my end. Come on now. Going straight, so I got Twitch up there. And my regular. Yeah, the video from Restream to YouTube doesn't seem to be as good as the other. Okay. Anyway, let's talk about conditional probability. Let's just jump right into it. One last check. Just want to make sure that my calculator, when I bring it over, we're able to see it. And if we go 0.25 times 0.3, whatever we get up there shows up. So now I'm looking on YouTube. I'm also looking on Twitch. Now, this is pretty boring at the start of it, but I just want to make sure I get everything set up straight on the stream itself. Yeah, anyway. Okay, so at the beginning of every stream, I've started doing what all the pro streamers seem to do. They talk about their layout. I'm streaming through Restream tonight, just doing this. It's not a podcast, just online office hours for my statistics courses. This particular one in summer meets on Wednesday nights. I make these videos and then I post them to our Moodle from YouTube. Certainly I put the Twitch link out there as well. And the reason that I stream out to these places is because if I try to use Microsoft Teams or anything at the college, you got to have an in and an out. Twitch is easy to get in and out of. YouTube's easy to get in and out of. So folks, I think, have a little bit better time, easier time getting in there. Get my stream deck. Okay. And my chats don't go to YouTube's. Okay. All right, so let me get this back up here and let's talk about knowing a murder victim. What a great topic. What a morbid topic to talk about on a Thursday evening. So I'm going to extend a few of these topics from last night. And then if anybody comes in from my class and wants to talk about the test that's coming up next week, anything from measures of center, variance, or position, we'll talk about that. If I get into a mode here and I feel like doing a few at the end, even though nobody's here, I might do a few just problems to prep for the test on Wednesday. Okay, let's talk about this. Conditional probability. So if I have a statement like this, which I'm going to rewrite because I don't like that. If I have a statement like this, the probability of event A occurring, given that event B already occurred, what does that look like? Okay, well, let's go right into the example here, and I'm going to pull my notes over so I can pull my context. I'm not going to write the entire problem up here, but I'm going to write as much as I think that folks need to know. So this particular problem is called knowing a murder victim. So again, we're working with conditional probability. Last night I emphasized quite a bit tree diagrams and sample space. We're going to talk about that again within the context of this problem. And again, if you come into the chat, just let me know. I've got my chat up now. So we're talking about knowing a murder victim. So here's the context. In a sample of 1,000 adults. Okay, there's part one. So in a sample of 1,000 adults, 300 stated that they know a murder victim. They know a murder victim. So we have a sample of 1,000 adults. 300 of those stated they know a murder victim. What percentage of that population knows a murder victim? Well, let's pull it right up here. 300 divided by 1,000. Not rocket science, is it? It's 0.3. So, the probability that you'll know a murder victim is 0.3. Okay? So that's if you know one. That means that the probability that you don't know a murder victim would be 0.7. So these are the numbers that we need to know, 0.7 and 0.3. Given this population, this sample taken from a population of 1,000 adults, 300 of those 1,000 stated that they know a murder victim. Based on that, we're going to infer back to the population. The probability that someone knows a murder victim is 0.3. The probability they don't know a murder victim is 0.7. So now let's go into some the questions. So let's find the probability that let me back up for a second. Let me retrace my steps. So, sample of 1,000, 300 stated they know a murder victim, no problem. From this, gosh knows, that was a sample. We're gonna choose four adults. And here's the question. Find the probability all four chosen know a murder victim. Okay? So find the probability that all four chosen know a murder victim. And remember, we're basing this on the previous. Hey, Noella, thanks for stopping by. I appreciate it. Just going over a few things from last night first, and then if I get a chance after going over a few of these things, or if anybody has questions, I'll go over stuff for the test next week. No problem at all. So yeah, appreciate you stopping by. So we're going. I'll backtrack for just a second. So the title is Knowing a Murder Victim. A very morbid title. We take a sample of 1,000 adults. We pull 300. No. Yes, the sample of 1,000 adults. Good gracious, I'm getting all turned around. Sample of 1,000 adults. 300 out of that 1,000 said that they knew a murder victim. So the probability that they know a murder victim is about 30%. The probability that they don't know a murder victim is about 70%. We're going to choose four adults, and we want to find the probability that all four chosen know a murder victim. Well, knowing a murder victim is 0.3. Okay. So I'm going to start with the tree diagram here. And I'm going to go, so this is the first adult. So they either know a murder victim or don't know a murder victim. If they know of a murder victim, that probability is 0.3. Remember, in this has to equal 1, and 0.7 is don't know. 0.7 plus 0.3 is 1, so we're okay with that particular outcome. So let's go to the second one. So for the second, if the first one knew a murder victim, and then we chose the second either knows or doesn't know. And if the first doesn't know, then the second is also either going to know or don't know. Now the same probabilities apply. I'm just going to write them out here. So we've got 0.3, 0.7 to don't, 0.3, and 0.7. Okay. Now we chose four. So just like talked about last night, it is easy sometimes to run out of room in this in the tree diagrams. But I know where I'm going here, right? So let me just, in the middle of this, change my problem. And the whole reason I'm changing is not because it's going to get overly mathematically difficult, but because I'm running out of room. So let me backtrack just a second, change this from 4 to 2. Again, the only reason I'm changing that is because I'm running out of room, and I want to use this room in the side here to show my work. So if I want to find the probability that all, well, I need to change this too. Boy, I'm just all over. We're going to choose 2 adults, find the probability that all 2 chosen know a murder victim. Okay. So we're just going to simply, these are consecutive events. We look to the first person that we chose. Do you know a murder victim? They say no. They say yes. Then we go to the second. Do you know a murder victim? They say no. They say yes. And in this consecutive event, to produce our sample space from these events, what we're going to have to do is use the multiplication rule. So if we want to find that they know a murder victim, then we're simply going to go, the first one knew, the second one knew. So that's going to be 0.3 times 0.3. We did this last night as well, but just in case you ever get turned around, it's very easy to do this. 0.09. I don't know if anybody can see that on the side. Just using my graphing calculator. So the probability that the 2 chosen know a murder victim will be 0.09. Now let's extend that to our original problem, even though I've changed the context by changing that 4 to a 2. And let's go, what would it be if we wanted to find the probability that 4 chosen know a murder victim? Well, it would still be multiplication rule. It would just be 4 of them because we'd be going up 2 more iterations here and here, right? On the tree diagram. So 0.3 caret 4, 0.0081. Okay, so hopefully you get the idea from that. So we built this from, but we used the multiplication rule and we built this from the tree diagram. So let me take this down and let me put the sample space together. The sample space from the 2-person choice. So the sample space would be, I could have no, no. I could have no, don't know. I'm going to go right below it here. I could have don't know, no. And I could have don't know, don't know. There's my sample space. So the probability of no, no, we figured that out, and that was 0.09. The probability of don't know is going to be 0.7 times 0.7, 0.49. The probability of no, don't know is going to be 0.3 times 0.7, 0.21. And the probability of don't know no is going to be 0.7 times 3, which is going to be the same thing. 0.21. Now, remember that the sum of my probabilities from this sample space have to equal 1. So if I have 21 and 21, that's 42. Plus 50, that's 92, which is really 91, plus 0.9 is 1. So this adds up to be 1. 0.09 plus 21, 21, 49. So the sum of those probabilities in the sample space do equal 1. So we're okay. So I don't know. I think I started out okay, and then I stumbled a little bit. It's been a long day at work. Just like you see me in class, it happens from time to time. So there we go. Let's talk about a card problem again. And let's talk about, in my notes, yeah, we'll do one like we did last night. Let's just do this. So we are going to, from a standard deck, of 52 cards, right? From a standard deck of 52 cards, we are going to choose 2 cards with replacement. And what that means is I'm going to choose a card, then I'm going to put it back in the deck, shuffle again, and choose randomly again. So from a standard deck of 52 cards, we're going to choose 2 cards with replacement. So what I want to know is what's the probability that we get a 10 given that we already got a 10. Okay, let's do that. So I choose a card. And remember what I said last night, when you're working with the theoretical probability of an event happening, that conditional item of choosing the 10 first does occur. Because you're trying to find the probability of what would it be if it occurred and it occurred. So you're not trying to find all the iterations around it. So we're going to use the multiplication rule here. So the probability of choosing a 10 is then going to be multiplied by the probability of choosing a 10 given that a 10 was already chosen. Okay. So the probability of choosing a 10, there are 4 in a deck of cards, and there are 52 cards in that deck, right? When we go to the multiply side, what's the probability that we choose a 10 on the second draw given that we already chose a 10? Well, it's an independent event again because we took that first 10 and put it back in the deck, which means we are still working with 52 cards and we still have the possibility of 4 10s. And just like last night, this is one that you'll do quite often, the 52 times 52, but 4 times 4 is just simply 16. 52 times 52 is 2,000 some, 2704. Okay, and that's even, so you could reduce that down. I've run out of room there. I'm just going to leave it at that. So from a standard deck of 52 cards, choose 2 cards with replacement. Probability of choosing a 10, given that we've already chosen a 10 in the first draw, equals exactly what I've got laid out here. Okay, so let me erase this out. I'll use the same context with a deck of cards. I think last night we were talking a little bit about poker, but not to any extent. We're staying very basic with this until we learn the ins and outs of both the addition rule and both the multiplication rule and the addition rule. So from a standard deck of cards, choose 2 cards with replacement. So we'll do another example, and what I'm going to do this time is I'm going to do what is the probability of choosing a jack given that, let me think a little bit. Probability of drawing a jack, given that, okay, let's go with the suit. Given that a club was drawn previously. Okay, so on 52 cards, you reach down, you randomly select one. It should be a club. Then you're going to put that club back, and then you're going to draw to see what the probability of getting a jack is. So it's the same idea from before. And the reason we're doing it the same way is because we're doing it with replacement. We draw that first card, we put it back in. So the probability of, the probability of drawing a club is what? Well, there are 13 clubs in a deck out of 52. And we're going to multiply that times the probability of drawing a jack, given that we already drew a club, right? In this case, the probability of drawing a jack is 4 out of 52 because whatever club we pulled out could be any club we put back in there. Could have been the jack of clubs, which really muddies the water. But we put it back. We did it with replacement, so no problem. So what we're looking at here is 13 over 52. That's the probability of drawing that original club on the first draw, times 4 over 52, which is the probability of drawing that jack, given that we've already drawn a club. So back to the handy dandy calculator. Nothing crazy here. 13 times 4. 52, which is a deck of cards, 13 in each suit. I mean, that's easy. And 2704. Excuse me. So there it is. Okay, now I'm going to just go in here and I'm going to change this up just a little bit. Oh shoot, what is that? Cut. Okay. So now we're going to go to without replacement. So from a standard deck of 52 cards, choose 2 cards without replacement. And remember, as I mentioned, the more and more that I teach it, I've been teaching this class for 20 years or so. The more I teach it, the more I see that students don't play cards like they used to, right? So getting used to working with cards, playing with cards, understanding the deck is important for this class, because especially for this section or this chapter, because I use during the probability section a lot of card not techniques, but a lot of card questions. So now we're looking at without replacement. So we are going to find, or we're going to look for the probability of drawing a, let's just go a queen, given that we've already drawn a king out. Okay. Well, what's the probability of drawing that first king? Well, the probability of drawing a king is just simply 4 over 52. Because there's 4 kings, there's 52 cards in the deck. The probability of drawing a queen, given that we've drawn a king, and remember, we don't put the king back. So the difference now is that I've got 51 cards, but I do have 4 queens. Because remember, when we're working with this theoretical conditional probability, the situation that we're looking at has occurred. So what's the probability of drawing a queen given that you've drawn a king? So we are going to assume that that did happen. Since that king happened, that's what we threw out, which means that there are 3 kings in the deck, but we don't care about that, other than it makes 1 less in the deck. That's the only thing we care about. But we have 4 queens. So now I do that a lot. Now we have 16 over, and instead of 2704, we're going to have a little different situation. 52 times 51, 2652. There's some interesting patterns there, but we're not talking about that tonight. Okay. So a couple of examples there. Let me see. Maybe I'll do... I don't know. I tell you what's interesting to me is I'm looking up at the YouTube stream, which is fine, but it is not as bright. Colors aren't as bright and vibrant as my Twitch stream. It's interesting. I may have to just go back to Twitch, but I'm trying to use YouTube because I'm putting calculator videos out as fast as I can. Not trying to hurry them up, but I mean, I do 1 or 2 a week, try to. Just some quick calculator videos on how to on the TI-84. And then I'm going to go back and do some ones that are about 1 to 2 minutes where I talk about it and where we kind of walk through it. Still not long videos, but a little bit more than just the super quick ones that I'm putting out on the shorts. So I don't know. I'm just trying to kind of keep it all together. Let's move ahead right here. And let's backtrack just a little bit. Let me go back. So started talking about conditional probability. We started this in class last night. We talked about the multiplication rule. I went into a ton of detail into the sample space and tree diagrams, using the tree diagrams, building the sample space, the range of probabilities rules, the law of large numbers, a lot of topics we talked about last night. So I wanted to start out talking about that. So I went with knowing a murder victim. We had a sample of 1,300 stated they know a murder victim. We pulled out the probability from that sample, and then we choose 2 adults. I started with 4, but I saw that I was running out of room, so I truncated it back. Find the probability that all 2 chosen know a murder victim. Excuse me. Built the sample space, talked about it in some detail, and then I went to some card problems. I've erased off from here, but I did with replacement, so choosing 2 cards. Choose a card, put it back. That's with replacement. What's the probability of drawing this, then that? And then I went to without replacement, or we choose a card, throw it out, or push it to the side. It doesn't go back in. It does not have a probability of being chosen again. And then you're trying to find some other card that you're drawing. So we talked about that. I think what I'll do now is I'll backtrack just a little bit. Back just a bit to what the test may look like on next Wednesday. So let me squeeze over here for a second. I wonder if I can copy and paste this on here. I'm going to try. If the screen goes black, and it Everything disappears. You'll know why. Let me see if I can. I wonder if I can paste this on there. Daggone it. I'm on Restream, which is a little bit different. I could just share the screen, but that's going to pull everything away. Oh, well, let me just draw what's on here. I'll just draw it out. That's less time than me staring at it, trying to figure out how to paste it into Restream, which I'm sure is not difficult, but I'm just afraid of tooling up the whole thing. So this is from a previous test that I wrote last spring. I think spring of 25, actually. So you've got heights of women have a bell-shaped distribution with a mean of 161 centimeters. Yeah. Okay. And I'm going to put SD for standard deviation, just so I don't have to write it all out. Standard deviation of 7 centimeters. Using our friend, the empirical rule, what's the approximate percentage? What is the approximate percentage of women between 154 and 168, 147, and 175, and then I've got another one greater than, sorry for the handwriting, I'm running out of room, greater than 182, and then less than 168. Okay, so heights of women have a bell-shaped distribution. Go back to my stream. Have a bell-shaped distribution with a mean of 161 centimeters and a standard deviation of 7 centimeters. Using empirical rule, our friend, what is the approximate percentage of women that fall between 154 and 168? Okay, so let's see, 161 and 7. So here's what we've got. We have a mean of 161, standard deviation of 7. It is a bell-shaped distribution, so we know it's following that symmetric normal curve, really. 154 and 168. So what percentage of women fall between 154 and 168? Well, let me draw this out. And here comes the old normal curve. See how good I can do this. That's probably the best curve I've drawn in a while. That's not too bad. A sketch of a normal curve. It's a bell-shaped distribution. Our mean right here in the middle was 161. Well, how many standard deviations are we away from the mean when we're in the middle? We are 0, so we're right smack dab in the middle. If we go out one standard deviation in that direction, and we go out one standard deviation in this direction, that's where we're sitting. Now, what do the numbers say about this? Well, that -1, this is just an index. It's just the distance from that 0. So both of these are a distance of 1. The negative just indicates that it falls below the mean in this particular curve. Yeah, I'm still here. I still see my streams up. Hopefully you can see me and hear me. I don't know. Noella was asking if I was still there. I feel like I am. Let me double check my voice. Yeah, I'm still here. Yeah, there it goes. You probably have a little bit of feedback there. Okay. So our mean was 161. So 161 plus 7 would be one standard deviation away. So we're at 168 here. And if we take 161 and subtract 7, that's like 160 minus 6, so it's 154 on the other side. Well, isn't that what we're trying to find, the distance? 154 to 168. Well, if you remember, I told you it's just 3 basic numbers for empirical rule. You got 68%, you got 95%, and you got almost all of it at 99.7%, right? The 68% is between one standard deviation on either side. That's where we are disconnecting. What is going on? Man. I'm not sure if it's... Let's see if it's back up. I don't know. Let me give it a second. I'll probably have to go right back over this. It seems to still be up. The YouTube seems to still be up. So if I throw my hand and wave, how caught up are we? That one still seems to be there. 154 to 168. Well, if you remember, I told you it's just... What is going on? Okay. It appears that I'm back. Okay, thanks, Noella. I don't know what happened. I had a single solitary glitch, and I had that with the Roku TV earlier too. So I don't know if it's my internet, if it's the weather coming through or whatever. So let me backtrack. So between here and here, this area right here is 68%. So when the question asked, what is the approximate percentage of women that fall between 154 and 168, the answer is 68%. Get all this off. Yay. So the answer is 68%, because 68% of my data falls here. Okay? So let's do the next one. I'm going to erase off 154 and 168. And I'm going to go to the next one, which was 147 and 175. So what is the approximate? What is the approximate percentage of women that fall between 147 centimeters and 175 centimeters based on our data? Well, I don't know. How many standard deviations away do they fall? Hopefully they use an empirical rule. Hopefully they fall within 1, 2, or something that we can work on. So if I go out 2, I got to go 7 more. So that's 170 plus 5. So I'm going to have 175. Well, that's one of my numbers. Yay. And if I go down here, if I go down 4, 5, 6, 7, that's 147. So that's easy. So the percentage of our data that falls between 2 standard deviations is 95%. And that 147 and 175 is what we're looking for. So the answer to that one would be 95. Easy so far. Is the next one easy? I don't remember my numbers from this. No, greater than 182. Okay, let's look at this one. So greater than 182. Well, where's 182 fall? Let's find out. Whoops. If we go out one more standard deviation, so in other words, we are at 2 and then 3. We are at -2 and then -3, right? If I take 175 and add 7 more because I'm going out one more standard deviation, then I go to 182. The next that we were looking at is what percentage of females in this population, if we just chose one randomly, what percent, or what would be the probability that that one would be greater than 182? Okay, that would just be here, all of this, right? Well, I don't know. Would it be rare? Would it be small? Yes, it would be very small. So if you're looking at greater than 182 or less than 168, put that one up here too. Whoops. So we're looking at situation number 1, situation number 2. Greater than 182. Well, if 99.7%, and let me pull this over. Let me do some magic manipulations here with the calculator, then I'll put it back. If 0.997 is what is between 3 standard deviations on either side, then what's left in the entire normal curve, 1 minus 0.997, would be 0.003. Well, we're only looking, that's what's left considering both sides. Well, we're only looking on one side, so you split it in half. So you say divided by 2. So 0.0015 would be the amount of area that would be greater, according to the empirical rule, that would be greater than 182. Now, if we're looking at less than 168, that's a little bit different. Let me erase some of this mess out from in here. And I'll color in just a little bit. Less than 168. Well, that's all of this, isn't it? Well, what do we know? Well, we know that from, this is going to get messy. We know that from the middle back, that's 0.5. And we know that from 1 to 1 is 68. Let me switch this back. We know from 1 to 1 is 68%, which means whatever we've got left right here is half of 68, which is 0.34. So we add that to our 0.5, and we get 0.84. We did one like this in class last night. All of this is just simply using the empirical rule and doing some subtracting and some adding based on what we know about this normal distribution. Or this bell-shaped curve. The bell-shaped curve has an area of 1 underneath it, right? It is asymptotic. It goes all the way to infinity and negative infinity on either side. But if we know, using the empirical rule, that 99.7% of the curve falls between 3 standard deviations, then we can figure out what's outside of that. If we know that 50% falls on either side of that median in the middle, which is also the mean, then we can figure out from there. And if we know that 68% is split between 1 and 1, then we know that from 0 to 1, it's 34 on both sides, or 0.34. So I know that was kind of a quick down and dirty at the end of this, but this empirical rule, we're going to do a ton of this once we get into the normal distribution. We're going to be a lot more precise. So I hope this helps a little bit. Okay. Let me do this. I'm going to pull in here. Let me see. I don't think I'm going to pull anything else in, actually. I think I'm okay. Okay. All right. So I think I'll end it there. I have been on for about 40 minutes. Not a long stream tonight. Just kind of a catch up from last night. I started out with some probability, conditional probability, nothing major, just a problem or two. Actually, I think I did 1, 2, 3, 4. I think I did 5 problems. And then I walked into this mess, which is working with empirical rule and answering a few questions based on some context. In this case, it was the heights of women in centimeters. So I think I'll leave it right there. Noella, thanks for stopping by. I always appreciate folks stopping by. If you haven't subscribed or left a comment or anything, leave one. It's kind of fun for me. I'm not a monetary streamer, just building a little bit of a rapport with my class and trying to do some online office hours in my own time that might help you. Might help you on Video Demand, or it might even help you on some of the stuff that we're doing in class from the stream itself. Might be able to ask questions. So, okay. I'm getting a little bit tired, so I think we're going to sign off for now. But again, Noel, appreciate you coming by. If anybody else came by, I appreciate it. I didn't see anybody in the hey, Offbeat, how you doing? I didn't see anybody from class in here other than Noella, unless Offbeat's in my class. Maybe they are. Maybe that's their YouTube sign in, or yeah, YouTube. So, but either way, I'm going to leave it at that. So we talked about empirical rule, just getting ready for the test next week with measures of center, variation, and position. And thanks, Offbeat. I appreciate that. I really do. And so we're getting ready for a test, and that's about it. And then we'll continue with probability. Don't forget that next week you've got a note sheet that I handed out, which is your vocabulary and formulas that I ask you to be able to study and regurgitate for a vocabulary quiz. We'll still have that quiz at the start of class before we take the test. I know that's mean, but I have to get that stuff in, and I have to have you studying each week, especially in a short, truncated summer session. So, Offbeat, I appreciate that a lot. I really do appreciate you stopping by. And Noella, if you're still there, I appreciate it. And thanks for sending the "You Still There" comment, because I had no idea that it had popped offline because I'm sitting here doodling. I didn't even know. So, all right, guys, I'll be back on next Tuesday. I'll probably be back on this weekend, playing some games. But as far as content here, maybe a little bit this weekend and probably some on Tuesday. Again, I'm rambling on. I'm getting tired, so I'm going to step off. Oh, Offbeat, I'll probably stream a little bit of gaming tonight from Xbox. Xbox or PlayStation, one or the other. I'll probably do a little bit of Dead by Daylight because it's a junky. I don't have to think too much about it, and I've played it for a while. So I'll probably do a little bit of that. And then stream again with statistics next Tuesday and Thursday for sure. And then maybe some this weekend if I get a few minutes just to pop on and leave a video on demand for my class. Or for anybody else that wants to pop on and ask questions and discuss statistics. So, all right, I'm going to sign off. Yeah, Offbeat, appreciate it. Noella, appreciate it. And anybody else who's in here, thank you. And I'll see you guys next time I'm on. Thanks.